Okay, so we're kind of recapping topic 11, which is topic 11 is called measurement and data processing. So really topic 11 is kind of all the different techniques that you would use when you are making measurements and recording data and doing calculations during labs, during experiments, okay? So it starts off talking about sort of different instruments, different equipment, and how to tell if something is precise. And so we'll kind of go through, we're going through only this 11.1 section today. There is an 11.2. It's not here in your note packet. I'm going to give you guys something separate, but top 11.2 really just covers like graphs, you know, how to do graphs, how to label graphs and all that kind of stuff, how to interpret graphs and how to create them. And then the 11.3 stuff is stuff that we won't get to until later because it has to do with like organic chemistry and some measurements with that. And we haven't learned that yet. So when we looked at this before Christmas break, we kind of went through all this. I'm going to kind of briefly recap it, but I really want to focus on the calculation part today because now that we have talked about topic 5, it's going to make hopefully more sense when we go through and look at the calculation together. But we need to know the difference between qualitative and quantitative data because both of them are important. Both of them should be in your lab write-up. Okay, qualitative is any kind of word sentence descriptions because it's non-numerical, so you're describing, you know, things like what does it look like, is it giving any noise, is it bubbling, is it, you know, temperature, can you feel it getting warmer or cooler, does it look like it's doing anything, okay, is it changing color, you know, all those kinds of things. Quantitative are things you're going to measure, so you could measure mass, you could measure temperature, you could measure volume, okay, you could measure pH if you're doing something with acids and bases. There's all different things. You can measure the time for something, okay? But anything you're measuring and you're getting a numerical value, that's quantitative. And so when you measure quantitative data, you always want to present it in tables. You want to make sure you have your correct units. And then you also have to have these things called uncertainties that we're going to get more into as we go through this topic. And we also talk about lab stuff because that's determined by the instrument that you're using. And also if you're doing something like time, then your human limitation, obviously, because your reflexes are not perfect. Okay. Propagation of errors in data processing. Okay, that's really what we're going to look at today, because that's usually the toughest part for people is applying all of this when you're actually doing calculations, and then looking at what impact the uncertainties have on your final answer, your final result from your calculations. Okay. We also need to know the difference between systematic error and random error. Random error, you can do more trials to try to reduce it. Systematic error, you can fix something's wrong with your experimental design. Okay, so like for example, maybe you need to insulate your container if you're measuring temperature and the temperature's not getting where you want it to be, okay, or something like that. So these are kind of the applications of skills, but I kind of mentioned we need to know the difference between these two terms. We need to make sure we record uncertainties in all measurements with appropriate precision. That's important because when you guys are doing your IAs, all your data tables have to include the uncertainty in them to the correct precision, which means the correct decimal places and things like that. And everything has to match, or they'll kind of dock you for points on that. Discuss ways to reduce uncertainties. That's your random errors. Propagation of uncertainties when you're doing calculations. So whenever it says process data, they're just meaning you're calculating something. You're taking the data you measured from your lab, and then you're using that data, you're processing it, and you're calculating something with it, okay? Systematic errors and their impact and how they can be reduced. So IB is really big on the scientific process. So, you know, you're going to design a lab, you're going to collect some data, you're going to process it and calculate some stuff, you're going to analyze it, make a graph, you know, all that stuff. And then when you look at all your stuff and you say, well, okay, based on this graph or based on this data, it looks like there's some systematic error. And then they want you to discuss, well, how could you fix that? Okay, so what could you go back to your experiment and what could you adjust or change that could fix it and reduce that amount of error? Is it going to have a major or a minor effect? And then calculating percent error when there is an accepted value that you can compare it to. Okay. So keeping that in mind, I'm not going to spend a lot of time going through this beginning part because it's covered in the videos that are already on Canvas. And also we did go over it at the beginning or at the end of last semester together. But basically, absolute uncertainty are going to be numbers. So if it says a number plus or minus a certain number of the unit, that's an absolute uncertainty, okay? Because that means that the mass that I'm measuring, for example, on this one is 16.43, but it could be 0.01 or grams lower or higher. So really it could be 16.42 or it could be 16.44. So it could be anywhere between 16.42 and 16.44. Okay. The actual number it's giving me is 0.43, but it has a range of uncertainty. Okay. Digital things are usually a smaller range of uncertainty because they're digital, so they're made a little bit better. Analog, where we have to read it like a graduated cylinder here, okay? The range of uncertainty is probably going to be a little bit higher. And in fact, on this one, you can see it's actually plus or minus 0.5 because on analog, it's always half of the smallest scale division. So on digital, you just look at how many decimal places does it measure to. So this one measures to the 100th place. So it's plus or minus 1/100th. Okay. On analog, like a graduated cylinder like this, you have to look at your scale. So this scale in here is going by ones, so because I can see a bunch of tick marks between 40 and 50. So since the scale is going by one, half of that is 0.5. And so that's why there's plus or minus 0.5 cubic centimeters here, because half of the smallest scale division on this piece of equipment is 0.5. Now, percentage uncertainty is taking that absolute uncertainty and just converting it to a percent. So you do the uncertainty divided by your actual measurement, and then you multiply by 100 to make it a percentage. And so both of those did that. Okay, this was 0.01, that's the uncertainty, divided by the actual measurement from our instrument, the 16.43, times 100. Okay, down here, 0.5 was the uncertainty, 43 was the measurement, multiplied by 100, and then here's our percentage. Okay. Now, those are important because those are going to directly apply to when we're doing calculations in our lab. So we're going to look at an example in just a minute. Quantitative and qualitative, I kind of went over this already, but basically numbers and not numbers, they're descriptions. Okay. When you record data, we went over this a little bit at the end of the semester, but I'm going to redo it again just because we are getting ready to start doing more of the lab stuff. Okay. So anytime you have a data table, quantitative unit data should have units and uncertainties. So you don't have, that doesn't mean you have to put it in every box. If you notice, because you want it streamlined, you want it easy to read. Okay. So what they've done here is they've done 4 different trials. So they've labeled them trials 1, 2, 3, 4. You have to do at least 3 trials on everything you do. And then here's what they're measuring. So they're measuring, this example is for a titration. So they've measured some different volumes because titration has to do with, giving a certain volume of solution and watching for a color change, and then using the data to calculate the concentration of an unknown solution usually. So on this one, the initial volume, notice they all started at 0. That's typical because that makes the math easier when you start at 0, okay? And then the final volume is here. And so then the total volume, that's the change. So all they did to get the third line, the total, they subtracted final minus initial. And so that's why on the third line, all the numbers look like exactly the same as the second, because our initial was all 0, okay? And then they also have the qualitative data. They have a color change here, and they have all of them labeled. Now, you should record qualitative data. If it doesn't fit in your table as nicely as this, you can write it out separately, like on a sentence underneath the table. That's fine too, as long as you're very clear that you're recording both qualitative and quantitative. Now, what I want to point out are the uncertainties and the units, okay? Notice here in the actual table, all they have are the numbers in here. So where are the units and the uncertainties? Well, they're over here because I don't need to put it in every box because everything on this first row, they're all going to have the same uncertainty. They're all measuring the initial volume. So I'm using the same burette, the same piece of equipment to measure all of them. So I know all of them are going to be plus or minus whatever half of the smallest division is. And so for this piece of equipment they used, the smallest division must have been 1/10 of a centimeter, because half of that would be the 0.05. And so I don't need to list this uncertainty in unit on every box over here. I just list it once on the row, and I know that that applies to all the numbers on this row. Same thing here, the final volume. Now here for the total volume, the number changed. The reason for that is called propagation of error. And so propagation of error is where we have to add our uncertainties together when we do calculations. And so on this row, the total volume, we found that number by subtracting. We subtracted row 2 minus row 1, and that gave us the values for row 3. So anytime you add or subtract numbers, you add their uncertainties together. So that's why this is 0.1, because we had to add these two uncertainties together from lines 1 and 2. Okay. Random errors and systematic errors, we'll come back to that later, but I really want to get down here to the propagation part. Okay. So this example, it says, in an experiment to measure the enthalpy change of a reaction, the following quantitative data was collected. So this table's set up a little differently. They have the trials going down the side, and they have the measurements going across the top. So you can set it up this way or the way the titration one was set up, as long as it's organized and it makes sense. Okay. So here's the initial temperature of water. Notice they have the uncertainty and the units here with that label. Here is the maximum temperature of water, same thing. Here's the units and the uncertainty. But then here on the change, notice that the uncertainty changed. Okay. That's because to get the change in temperature, remember delta T, we always do final temperature minus initial temperature. So they had to subtract these two numbers in the first two columns to get what's here in the last one. And anytime you add or subtract numbers, you always add their absolute uncertainty together. And so what they did is they did 26 minus 18.5. That gave them 6.5, but really it's 6.5 plus or minus 1.0 degrees C. So that means it could be as low as 5.5, or it could be as high as 7.5. That's the range based on our uncertainty of our instruments. So now the question here says, use this data to calculate the enthalpy change. Okay, so this is why this might hopefully make a little more sense now, because we're going to have to calculate delta H, which is excuse me. We're going to calculate Q, I'm sorry. So Q is, remember, MC delta T. So delta T, they've already calculated. Delta T is over here in this last column. Okay, those are the delta T's. C, that's our specific heat. And they say right here we're using water. So we're going to use the specific heat of water that we talked about in our notes. And then up here on top, they give us the volume of water in the calorimeter. So that's important, because if you remember from last week, I told you guys that when they give us the volume of water, that we pretend that's the mass, because we know the density of water is 1 gram per cubic centimeter. So we know that if they say there's 50 cubic centimeters, we know that really means there's 50 grams of water. Okay. Here's what you want to do though. I don't want to do 3 separate calculations. I want to do 1. So before I do the calculations, I'm going to average my delta T's together. I'm going to average my temperatures. So if I average, the uncertainty will stay the same. Okay. So let me erase this from average before we get into that. Okay. So I have 6.5 plus 7.0 plus 8.0. Let's see, that's 15. 21.5, I believe. So 21.5, and then divide by 3, because that's the number of values that I added up. And what was that, 7 point something? 21.5 divided by 3. 21.5 divided by 3. So I get 7.16, and then the 6 kind of keeps repeating. So we're just going to round it to 7.2. And the reason I'm going to round it to 7.2 is because I want to keep my precision the same. So if I look back up here in the problem, all my temperatures were rounded to 1 decimal place, okay? So I'm gonna keep it the same number of sig figs, 2 sig figs, 1 decimal place. So my average temperature is 7.2, 7.2 plus or minus 1.0 degrees C. So notice how I still kept the uncertainty. The reason that number didn't change is because if I were to add up 1 plus 1 plus 1, that'd be 3 divided by 3, that's still 1. So the uncertainty is not going to change if you average numbers. It'll still be the same. So this is the number I want to use for delta T because that's going to be my average. And I always want to average my number. That's why we do multiple trials. So for every different experiment, you have to do at least 3 trials so that you can average your data to have better results, but more precise. The more trials you do, the more you reduce your random error. Okay. So now we're going to go back to the Q equation because that's going to allow us to do enthalpy. So Q is MC delta T. Here's what we're going to use for delta T. 50 up here is what we're going to use for mass because that's the volume of water, which we talked about is equal to the mass of water. And then C is specific heat, and we can look that up in our notes or our data booklet. Okay. So I'm going to come down here and I'm going to plug everything in. Q equals the mass is going to be 50. C in your notes is 4.18. Delta T is 7.2. Okay. So if I multiply all of these, I get, let's see, 50 times 4.18 times 7.2. I get 1,504.8. Remember, Q always comes out in joules. Okay. Now, I'm not quite done because that's just the calculation. So, which is what kind of we've been practicing in our notes and stuff, the last week or so. When you're actually doing this in a lab, you have to pay attention to your uncertainties. So I have to come back up here because there's going to be a little bit more to the calculation. So I have to use this plus or minus 1.0, that's the temperature. And then my mass, if you notice here, they gave us the volume, but we used it for the mass. It has an uncertainty, plus or minus 0.5, okay? So what happens is because I multiplied these numbers together, M and delta T, when I multiply values, in order to figure out the uncertainty for the answer, I don't add together their absolute uncertainties like when we add or subtract the numbers. I have to add together their percent uncertainties. Okay. So this is where it's always like a little tricky at the beginning for people because people have trouble doing this many steps. Okay. It's not that it's hard. It's just you got to remember all the different parts to do. And that gets tedious for people and people forget to do stuff. So what we just did, what I have written here in blue, that's the answer, but I'm not done yet because I have to propagate my error. I have to propagate my uncertainty. And so that's what you're doing here we are going to take the uncertainty of the mass, which they told us up here was plus or minus 0.5. So in order to find the percent, I'm going to do that 0.5 because that was for the mass. I'm going to divide by the measurement. Okay. Now the measurement on this, it was volume, technically not the mass, but it was a 50. It was 50.0. Yes. So remember to do the percent uncertainty, I do the absolute uncertainty, which for this measurement was 0.5 because it was plus or minus 0.5 up there. I divide it by the actual number I measured, which for this one was 50.0. I multiply by 100. That's going to give me the percent uncertainty of the mass, which is actually that volume that they gave us in the problem. So 0.5 divided by 50 and then times 100. That gives us 1%, okay? So 1% for the mass, okay, which came from the volume. Now, delta T, I have to do the same thing. Any numbers I have measured that have uncertainties, I have to do this for, okay? So I'm going to go ahead and I'm going to put an M here so we know that's the percent for the mass, because now we have to do the percent for delta T. Now for delta T, we'll come back up here and look at our average. The uncertainty was plus or minus 1. So on top, I'm going to have a 1. Now on the bottom, we averaged, and we're going to use the average value, 7.2. So 1 divided by 7.2 times 100. Now on this one, we get 13.88888, and the 8 kind of keeps going. So I'm going to just round it up to 14%. So it's a whole number. So here's, now that they're both percentages, now we need to add them together. You always add your uncertainties. It's just when we multiply or divide our numbers, we add the percent uncertainties like we're doing right now. When we add or subtract numbers, we add the absolute uncertainties. So that's why a lot of times in your data, when I have something like initial temperature and final or maximum or final temperature, in order to get the change, I just subtracted to get these numbers. And so I just added 0.5 plus 0.5. That's where this 1.0 for the change came in, because I added the two 0.5s just straight together. I didn't have to convert them to percentages, but that's because I only had to subtract to get these numbers. So adding and subtracting is a lot easier because I can just add together the absolute uncertainties. Multiplication and division, like what we're doing here on the Q equation, because this is all multiplication, I have to add together percent uncertainty. So that's why we're having to take this extra step of converting these numbers they gave us that were the absolutes to percentages. Now that I have both of them, and C, the reason we don't have to do this for C is because C is a constant. It's not a measurement that we did in the lab. Okay, we measured the volume to use for the mass, and we measured the temperature change with our instruments. So I'm going to add these up. So total, I have 15%. Okay. So what that means, if I rewrite my answer that we calculated was 1,504.8, right? 1,500, yeah, 1,504.8. And then it's going to be plus or minus 15% of joules, okay? But they don't want us to leave it in a percentage. So I have to figure out, I have to convert this percent right here back to, I have to convert it back to an absolute uncertainty for my final answer. And so in order to do that, I have to figure out, well, what is 15% of this number, okay? And so I have to say, I have to do kind of like a little bit of a calculation. I have to say, well, 15%, that's 15 out of 100, right? That's what a percentage is. So 15 out of 100, and I'm going to multiply that by my value that I calculated. And that gives me, I haven't done the calculation yet. So that gives me 225.72. And so to finish this, what I would finally write it as is I would write 1,504.8 plus or minus 225.72 joules. So that's like my final answer. And I actually would probably round it a little bit better. I didn't really pay attention to the sig figs. We'll get into that more next time about being a little bit more specific with the sig figs. But for right now, that's what I would do. Just know that in the future, they'll probably round off a little bit better than what I did just now. All right, so